Hey everybody, my name is Chris, and I'm a tutor here at Chegg.com. I mostly do math and computer science, and in this video I'd like to talk to you a little bit about curvilinear coordinates. So what are curvilinear coordinates? Well, before we talk about that, let's talk about something that we're probably all already familiar with. That's the rectangular, also known as the Cartesian coordinate system. So we can have rectangular or Cartesian coordinates. So let's go ahead and review this real quick. So for the rectangular or the Cartesian coordinates, we have our xy plane. So let's go ahead and draw our x-axis here. Here's our x-axis, and here's our y-axis. And let's say we have a point all the way out here. Okay, so let's say this is the point 5, 4. Okay, so when we have a point in the rectangular or the Cartesian coordinate system, in a two-dimensional plane like this, it's two-dimensional because we have two axes, the x-axis and the y-axis. This first coordinate is called the x-coordinate. The second coordinate is called the y-coordinate. So 5 is the x-coordinate, 4 is the y-coordinate for this specific example here. So what does this 5 represent? Well, what it means is we go 5 units in the x or the horizontal direction. And the 4 means we go up 4 units in the vertical direction. So 5, 4. Okay, so that's how we represent this point in the rectangular or the Cartesian coordinate system, and that's how we interpret the coordinates. So the 5, the x-coordinate means 5 units in the x or horizontal direction, and the 4 means 4 units in the vertical or y direction. Now, there are other ways of expressing the location of this point, and that's sort of where this curvilinear coordinate system comes in. So the word curvilinear does not actually refer to one specific coordinate system in the same way that this does, but really curvilinear is sort of a general term that describes many different types of coordinate systems that we could have. And we'll talk about some of them in this video. So what are they? Well, another type that we could have is polar coordinates. So polar coordinates, those are another way of expressing a point in the xy plane. We could also have cylindrical coordinates. And cylindrical coordinates, those are a three-dimensional generalization of polar coordinates. And spherical coordinates, we could also have those. Okay, and spherical coordinates are also three-dimensional, which is not surprising given that a sphere itself is three-dimensional. So why might we want to have other coordinate systems if it seems like this is fine right here, expressing this as 5, 4 seems perfectly fine? Why do we need anything else? And the reason is that it really depends on your application. So if you're doing something, let's say in engineering or physics, and you're analyzing something where the geometry of your object that you're analyzing, maybe it's a circle. So let's say you're doing something for engineering and you're analyzing the heat flow across a circular plate. Well, for circular objects, using polar coordinates is much, much better than using rectangular coordinates. So polar coordinates will greatly simplify all the calculations that you have to do. So, and similar things can be said about cylindrical and spherical coordinates. If the geometry of your object or your scenario is more cylindrical, then use cylindrical coordinates. If you're dealing with something spherical, use spherical coordinates. No surprise there. So that's why we want to have different coordinate systems, is because some of these might be more convenient depending on our application. Okay, so continuing, well, let's go ahead and talk about polar coordinates. So remember we said that polar coordinates, that's another way of expressing a point in the xy plane. So if we have our point 5, 4 here, how would we express that in polar coordinates? Well, so I'm not going to give specific numbers for this, but I will tell you how to find them. For polar coordinates, we're going to have, instead of x, y, we're going to have r, theta. So we'll have r, theta. And what are r and theta? Well, r is the distance between the origin and the point. Okay, so r is this distance here. Okay, and what about theta? Well, theta measures the distance between, or sorry, the angle. Theta measures the angle between the positive x-axis and this little line segment right here. So that's what theta measures. So that's how we express points in polar coordinates, r, theta, where r is the distance from the origin to the point, and theta is the angle made by the between the positive x-axis and the line segment connecting the origin to the point. So I drew this in the first quadrant, but this is true in any quadrant, first, second, third, and fourth. It's also true on both of the axes. Okay. Now, if you have a point that's on the positive x-axis, like over here somewhere, then theta would just be 0, because the angle between the positive x-axis and this line segment is just 0. And that's perfectly okay. Okay, so, and like I said, we're not going to find these numbers specifically for this example, but I will tell you how to find them. So how do we find them? Well, notice what we have here. This little figure that I'm tracing, what is that? That's a right triangle, right? So we have a right triangle. Here's our little right angle. So we could actually use the Pythagorean theorem and say, okay, 4 squared plus 5 squared equals r squared. And then we could solve for r. And when we take the square root of both sides, we'll have a positive and a negative root. But you always want to take the positive root because r is measuring a distance. R represents a distance. So we always take r to be positive. Okay? And how do we find theta? Well, if we remember our right triangle trigonometry, tangent of theta is equal to 4 over 5 in this specific case. Okay, tangent is opposite over adjacent, 4 over 5. So we can say theta is the inverse tangent of 4/5. And we can put that into a calculator or something and we can figure that out. Now, that works so nicely because this is a point in the first quadrant. If the point were in the second or third or fourth quadrant, we'd have to do something a little differently. We'd have to be a little more careful. But it still follows from the basic fact that tangent is opposite over adjacent. Okay? So anyway, that's just a brief overview of polar coordinates. Now, what about cylindrical coordinates? Well, before we move on to cylindrical coordinates, there's actually not much I want to write down for that. I don't want to spend too much time on cylindrical, but I would like to do a specific example with spherical. So for cylindrical coordinates, remember, we said that that's a three-dimensional generalization of polar coordinates. So if we're in 3 dimensions, what do we have that's different? Well, in 3 dimensions, we have an x-axis, a y-axis, and then a z-axis. So you can imagine sort of a z-axis coming out of the page towards you is what we would have. Now, when we draw 3 axes, let me go to page 3 here. When we draw 3-dimensional coordinate systems, we actually do it a little bit differently. So here's our x-axis. Here's our y-axis, so x, y, and then here's our z-axis. Okay, so for cylindrical coordinates, it's really the same idea as polar coordinates, except now we just have this extra z coordinate. Okay, so for cylindrical coordinates, those are represented by r, comma, theta, comma, z, where r and theta are actually the exact same thing as before. So let's say we have a point that's sitting up here. Okay, you have a point sitting up here, and this point has a distance from the origin. Okay. Now, I would like to point out that it sort of looks like I'm drawing this in the YZ plane, but I'm really not. I'm sort of drawing it just floating out here in space, kind of sort of in front of the YZ plane. So if I were to drop a perpendicular down, it would hit the XY plane, say, somewhere over here. And then we would have this going out here. Okay, and this is a right triangle right here. And R is this distance, go ahead and fix that. R is this distance right here. This here is R. All right, and theta is the same thing it was before for polar coordinates. Theta is the angle made between this point and the positive x-axis. Okay, so R and theta are the same thing as before, but what about Z? Well, Z is actually just the height. And actually, z is the same thing that it would be in 3-dimensional rectangular coordinates. So for 2-dimensional rectangular coordinates, we just have x comma y. For 3-dimensional rectangular coordinates, we would have x comma y comma z. Okay, and as it turns out, z is the same thing in 3-dimensional rectangular coordinates and cylindrical coordinates. So that's why we say that cylindrical coordinates are really just a 3-dimensional generalization of polar coordinates, because we still have r and theta doing pretty much the same thing that they do for polar coordinates, but now we have this extra coordinate z, which again is just the height above or possibly below the xy plane. All right, now what about spherical coordinates? Spherical coordinates are a little more complicated, so let me draw a picture. Let's say we have our x-axis again, and then we have, go up a little more, We have our y-axis here. And then here's our z-axis. So again, let's say we have a point, let's say maybe somewhere over here. And then this point has a distance. There's a distance from the point to the origin. And I want to drop a perpendicular here onto the xy plane. So again, this is a right triangle. Okay, now for spherical coordinates, so it is three-dimensional, so we still just have three coordinates, but what we have is actually three Greek letters, rho, theta, rho, theta, and phi. Sometimes pronounced phi, but I think the proper pronunciation is phi. So this is rho, R-H-O, and this one is theta, T-H-E-T-A, and then this one is phi, P-H-I. Okay, so we have those three Greek letters there. So you might be looking at this picture and wondering, okay, what are these things here? What do they represent? Well, rho sort of takes the place of r. So rho is just this distance here. So rho takes the place of r from polar and cylindrical coordinates. So you might be asking yourself, why don't we just use r? Well, this is sort of the standard that has come to be throughout the years. And then what about theta and phi? Well, theta actually represents the same thing that it has been all along. Theta represents this angle between the point and the positive x-axis. Okay. Now, what about phi? Well, phi is the new thing here, and what phi represents is the angle between the positive z-axis and the point. Okay, so phi represents this angle here. So rho is a distance from the origin. Let me move this ever so slightly, make that eraser bigger, so that we can keep rho and phi a little bit further apart, so this isn't too confusing, hopefully. Okay, so this is rho right here. Rho represents this distance. Okay, and phi represents, again, the angle between the positive z-axis and the point. And theta represents the same thing it always has, the angle between the positive x-axis and the point. Okay, so that's how we express points in spherical coordinates. Now, what I want to do is an example where we convert from spherical coordinates to rectangular coordinates. So how do we go about doing that? Well, there's a formula that we could use. Okay, and the formula, it's pretty straightforward. It's really just a matter of knowing our trigonometry. So here we have rho, theta, and phi. Okay, and our point is 2, pi over 6, pi. Right, so convert these coordinates from spherical to rectangular. So how do we do that? Well, the formula we want to use is, well, basically, we're converting to x, y, z, right? So rectangular coordinates is x, y, z. And the formula says x equals rho sine phi cosine of theta. Y equals rho sine phi sine of theta. And z equals rho cosine of phi. Now, if you're wondering where this formula, or where these formulas come from, that's a little complicated. It's best suited for another video because it would make this video way too long. But here, I'm just going to show you basically what happens when we convert from spherical to rectangular. And again, it's just a matter of knowing the unit circle. So here's rho. Rho is 2. Theta is pi over 6. Phi is pi. So we just want to plug all this stuff into here and see what happens. So x, using this formula then, x equals rho sine phi cosine theta. So x is 2 sine of phi. Phi is pi. So that's 2 sine of pi times the cosine of theta, and theta is pi over 6, so times cosine of pi over 6, equals what? Well, 2 is just 2. What's the sine of pi? If we know our unit circle, we know that the sine of pi is 0. So this is 2 times 0 times, who cares, because now everything is 0. So we don't really care anymore what the cosine of pi over 6 is because we're just multiplying it by 0. So the x-coordinate is 0. Now what about the y-coordinate? Now for the y-coordinate, we have rho sine phi sine of theta. So again, we have 2, that's our row, multiplied by the sine of phi, and phi is pi. So we have 2 sine of pi. We're going to have 0 again, it looks like. And then multiplied by the sine of theta. And theta, again, is pi over 6. Not that it matters. And why does that not matter? Because, again, we have sine of pi, which is 0. So we end up with 2 times 0 times sine of pi over 6. But who really cares? Because we just end up with 0. Now, if you're curious, sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. All right, now what about z? Well, z is rho cosine of phi, so a little bit simpler. So z is 2 times the cosine of phi, and again, phi is pi. So times the cosine of pi, and if we know our unit circle, we know that the cosine of pi is -1. So this is 2 times -1, which is -2. So if we want to convert this point 2 comma pi over 6 comma pi from spherical to rectangular, then we are going to end up with the point 0 comma 0 comma -2. Okay, and that's what happens there. Now you might be wondering, well, hey, isn't 0, 0, -2 way simpler than this? Why would we even want to bother with that? And again, it's for the same reason that we mentioned before. It really depends on your application. It depends on the geometry of your situation. If you're doing a physical application where you're dealing with a three-dimensional object that's spherical, then it's going to be a lot easier to use spherical coordinates. So even though some points on the sphere might be more easily represented in rectangular coordinates, working with the object overall is going to be much easier using spherical coordinates, because spherical coordinates, as the name suggests, they're much more suited to working with spherical objects. Okay, so this has been an introduction to curvilinear coordinates. I hope you found this intro helpful, and thank you for watching.